Okay, 2.5, derivatives of quotients. So in this lesson, we're given functions that are quotient functions. So it's a function over top of another function. It looks like this. Quotient function f of x equals, or let's call it q of x. Q of x equals f of x over g of x. Okay, that is a quotient function. And we have a little rule here for differentiating them. This will again make a lot more sense once we do a few examples, but if we have q of x, which equals f of x over g of x, so if q of x is a quotient function where f of x and g of x are differentiable, and the derivative of g of x is not equal to 0, because then it would be undefined. If that is true, then q of x, and this is getting into our strategy for differentiating it, but q of x can be expressed as, I'm just going to write q of x equals f of x times, with a bracket, g of x, close bracket, to the power of -1. All this is doing is expressing our function from the denominator with a negative exponent. So 1 over x equals x to the power of -1. That's all that's happening there. In which case, if you take a look at this, what do you see? Well, we have this whole function then, becomes, and I can actually draw that on top. This is now the product of two functions. So this is now the product of two functions, which means we can apply the product rule. So apply the product rule. And if we look at it a little bit further, we can look at what we've done here with g of x to the power of -1. We've actually created a composite function. Composite function. So we can apply the chain rule. So that's essentially our steps to differentiating a quotient function. We're first going to take the denominator and express it as a product, which means we can apply the product rule. And then one of those functions is a composite function, so we're going to also apply the chain rule. And what happens is that the derivative of q of x becomes, and this is going to look kind of ugly, but basically what we're going to do is take the first function, f of x, times the derivative of the second function. But the second function is a composite function. So in taking the derivative of the second function, we're also going to apply the chain rule, which looks like this. Take the derivative of the outer function with respect to the inner function, which drops our exponent to -2. So now what we've done is we've taken that exponent, put it out in front, and dropped the exponent 1. So we've taken the derivative of the outer function with respect to the inner function, and we're going to multiply it by the derivative of the inner function. And then to finish off the product rule, the second part of the product rule then would be to add the derivative of the first function times the second function. Okay, so right here, that's chain rule. and this whole thing, all right, is the product rule. So it's the chain rule inside the product rule, essentially. Take a second to think through that, and as we do our examples, the first example for sure, I'm going to write it kind of step by step. What step are we working on? And then we'll get through this differentiating quotient functions business. At the same time, we're going to need to pay attention to what's happening to g of x, because g of x and its derivative cannot equal 0. So we're going to have some restrictions on g of x as well. Okay, example 1, we are going to differentiate. Example 1, differentiate q of x, which equals, in the numerator, 6x minus 5, in the denominator, x cubed plus 4. Now this is a simple example because the exponent of the denominator is 1. Right? The function g of x in the denominator has an exponent of 1 raised to the first power. So it's a little bit easier. We're going to state the domain and also differentiate it. So we'll do the domain at the end. We'll differentiate first. Here's q of x. Step 1. I'll write the steps. Sure, we'll write the steps here. Step 1. We are going to express q of x as a product. So we've got q of x, and now instead of having a quotient, we're going to take our numerator, 6x minus 5, brackets, and we're going to multiply it by the denominator to the power of negative 1. Now we're doing what we said in our notes. We're going to apply the product rule. Apply product rule. All right. So what we're doing is we're taking the, and I'm going to probably need more space here, but we'll see if I scoot over and write small. We're going for q prime of x then. The derivative of q of x is the derivative of the first function times the second function plus the first function times the derivative of the second function. Okay, so I haven't actually differentiated anything. I'm just kind of stating what we need to do. All right, now we can go through this bit by bit. The derivative of 6x minus 5 is just 6. It's going to be multiplied by the second function, 3x cubed, x cubed plus 4 to the power of negative 1. Then we have our first function, and for this part we are applying the chain rule. So when in applying the product rule, in actually differentiating this thing, we're going to apply the chain rule. We're applying the chain rule because we have a composite function here that needs to be differentiated. What does that mean? Okay, we're going to take the derivative of the outer function. Well, the outer function is x to the power of negative 1, okay, with respect to g of x, or whatever we wanted to call this function on the inside, with respect to the inner function. So what we're going to do is take that exponent out in front. We have negative 1 as a factor. Then we're just going to copy down our x cubed plus 4. X cubed plus 4, that's the inner function. And our exponent has now become negative 2. Then we're going to multiply by the derivative of the inner function, which is 3x squared. And that is the chain rule. From here, if you look at it, you note that this term, so now we have two terms, right? There's a plus sign in between, so we have a term here and a big ugly term here. Well, in this term, there's a x cubed plus 4 to the power of negative 1, and here we have x cubed plus 4 to the power of negative 2. So they have a common factor, and they actually have more common factors. They have a common factor of 3, because 3 can be divided out of this term. This has 3x squared, and 3 can be divided out of this term because it has a 6. So let's pull out this common factor for look for common factor. So this is the part, a new part, really. Common factor in this case is 3 times x cubed plus 4 to the power of negative 2. If these exponents were positive, you'd only pull out one of the factors. I guess negative exponents work the opposite way. You'd pull out the highest number, which is actually the lowest value. It's probably not making a ton of sense, but we'll see what happens here when we pull it out, when we factor it out. So now we've got a square bracket. We're going to end up with a binomial in here still. We have pulled out a factor of 3, so we're left with a factor of 2. And okay, a good way to think about this is, what do I need to multiply against this piece right here in order to get back to this piece right here? And if we're thinking about our rules of exponents, then it turns out that one factor, x cubed plus 4 to the exponent positive 1, times the same to the exponent of negative 2, ends up getting us this factor to the negative 1, if that makes sense. So if I can do that just off to the side, x to the power of negative 2 times x to the power of positive 1. In this case, we're multiplying powers with the same base, so we're just adding exponents. So if we need x to the power of negative 1, which is what we're factoring, and we factored out x to the power of negative 2, then this is the term that we need to multiply against to get back to the original. Okay? Next, over here. What do we have left in this term? If we pull out x cubed plus 4 to the power of negative 2 and the factor of 3, we are left with 6x minus 5 times negative 1, and the only other thing that's left is x squared. Okay, so this whole piece got factored out. From here, we're going to expand and simplify just the part that is easy to do. So just this inside this bracket here, we're going to expand and simplify, and it might take us a couple steps. So the outside stays the same. We've got 3 times x cubed plus 4 to the power of negative 2. And then inside this square bracket, this first term is pretty easy. We're just going to distribute the 2 to both terms. So we've got 2x cubed plus 8. And then here, we're going to, I'm going to leave that sign out. I'm going to do this all in one step. So I'm going to ignore the negative 1 at first. I'm just going to distribute the x cubed to both terms in the binomial. And then I'm going to note that it's all getting multiplied by negative 1 as well. So both of the signs are going to change. So 6x times x squared is 6x cubed. It's going to be negative because of that negative factor, so negative 6x cubed. And then negative 5 times x squared is negative 5x squared, but it's going to flip the sign, so it's going to be positive 5x squared. And then we can group like terms here, and at the same time, so maybe we can write some more steps. We're going to expand and simplify. So expand is what we did. Simplify is what we're going to do next, kind of group like terms. And then we're also going to express as a quotient. So we're going to flip this back into a quotient because we have a negative exponent. You could also say express as, or express with positive exponents. So I'm splitting this into a quotient, so I'm just going to draw my division line. And anything with a negative exponent is going to get bumped into the denominator, which is just x cubed plus 4 to the power of 2. In the numerator, we have a factor of 3. And then I'm going to group my like terms. So I have my x cubes, I have negative 6 and positive 2. That's negative 4x cubed plus 5x squared plus 8. And that is q prime of x. And next thing we were asked to do is note the restrictions. So step 7, note restrictions on q of x. So q of x has x cubed plus 4 in the denominator. So since the denominator can't be 0, x cubed plus 4 can't be 0. Subtract 4 from both sides. X cubed cannot equal negative 4. And because it's a cube root, this still works, right? If it was a square root, you can't take the square root of a negative number. But you can take the cube root of a negative number because there will be 3 factors, which if it was negative, it would result in a negative value. So how do we write this? We just write x cannot be the cube root of negative 4. That's a restriction on the domain of q of x, and that is shared by the derivative q prime of x. Therefore, domain of q of x and q prime of x is x belongs to the set of real numbers, but x cannot be the cube root of negative 4. Okay, running through it really quickly one more time. We get a quotient function, q of x, f of x over g of x. We're going to express it as a product. So g of x, rather than being in the denominator with a positive exponent of negative 1, you can kind of picture it like 1. Okay, with a positive exponent of 1, we're going to put it in the numerator with a negative 1 exponent. Then we have a product. So a function that is the product of 2 functions, and one of those functions is a combined function. So we're going to use the product law, and then when it comes time to differentiate our second function, we're going to use the chain rule, inner, outer. And from there, it is algebra, being careful, simplifying, expanding, simplifying, look for a common factor. That's going to allow us to put this thing back into the denominator, which is what we did in the last step. And then the domain of both is dependent on the domain of q of x. Q prime of x will be undefined everywhere that q of x is undefined. I should close that off. Example 2, we are going to differentiate q of x. It's a quotient function. In the numerator, it's x plus 3. In the denominator, we have the square root of x squared minus 1. We're going to follow the same steps to differentiate this and also note restrictions by finding the domain. So, step 1, express q of x as a product function. Q of x equals x plus 3 times, and by the way, at the same time, we're not going to use the square root. We're going to express that as a exponent of 1/2. So in the numerator, as our product, it's going to have an exponent of negative 1/2. So you can see how this one's going to be a little bit trickier, paying attention to our fractional exponent.
What does on the exponent?
Okay, from here we apply the product rule. So what we're saying is we're just kind of stating what the derivative is and how it's built without actually differentiating at this point. So the product rule says take the derivative d over dx, d by dx, of the first function, multiply it by the second function. Add the derivative of the second function, or the first function not derived, so the first function as is, times the derivative of the second function. All right, there's the product rule. Now we're going to actually differentiate this. The first step is pretty straightforward. The derivative of x plus 3 is just 1 times x squared minus 1 to the power of negative 1/2. And for the second part, we're going to copy down our first function, x plus 3, and then we have the chain rule because we have a composite function. So we're going to take the derivative of the outer with respect to the inner, and then multiply it by the derivative of the inner. So the derivative of the outer is negative 1/2 with respect to the inner, x squared minus 1, and our exponent is going to drop 1 to negative 3/2. And then we still need to multiply by the derivative of the inner, which is 2x. All right, there's product rule and chain rule taken care of. Now we are looking for a common factor. Which is going to be x squared minus 1 to the power of negative 3/2. X squared minus 1 to the power of negative 3/2. There's no numerical common factor because we just have a 1 here. Okay, so we're pulling out x squared minus 1 to the power of negative 3/2. What does that leave us with? Here, it's going to leave us with x squared minus 1 to the power of 1, because if we're multiplying powers with the same base, we're adding the exponents, and we should get back to negative 0.5, and we're at negative 0.1.5. Sorry, negative 1.5 plus 1 is negative 0.5, or negative 3/2 plus 1 is negative 1/2. So that's all that's left from this first term. And then we're going to add and see what's left in the last part. We've got x plus 3, negative 1/2. This whole thing is gone, and we still have a 2x. And then from here, we're going to expand and simplify as much as possible. So out front, we still have our x squared minus 1 to the power of negative 3/2. That is going to, in the next step, jump down into the denominator because it has a negative exponent. But the rest of this this part is good, x squared minus 1. And we're probably going to leave that plus sign out. I'm going to do the same thing as before. I'm going to do this all in one step. So essentially I am going to, well, let's do this first. 1/2 times 2 is just x. So this is going to be negative x. It's going to get distributed to both of the terms in the binomial. So we've got negative x times x. That is negative x squared. And we have negative x times 3, which is negative 3x. Probably could have done this step at the same time. If we look at this, I should recognize this as a difference of squares. Wait, nope, that's false. It's to the power of 1, which means I actually don't even need these brackets. So that's, all right, x squared minus 1 minus x squared minus 3x. Yes? Good. 2 steps in one here. We're going to group our like terms and bump this guy down into the denominator. And we're going to express it as a root again. I'll do the numerator first because that's easier to see. We've got x squared minus x squared. They cancel out. So we have negative 3x minus 1. And then in the denominator, we have, and you might need to go back and practice how to express fractional exponents as roots. But we have the square root of x squared minus 1 to the power of 3. Last thing we need to do is note the restrictions on q of x to get the domain. So, since the denominator cannot be 0, x squared minus 1 must be greater than 0. It also must be positive because there's no such thing as the square root of a negative number. So we've got x squared minus 1 is greater than 0. And that means x squared must be greater than 1, which means x, there's 2 answers here, 2 possibilities, because negative 1 squared is 1, and 1 squared is 1. So x has to be less than negative 1, or x has to be greater than positive 1. So the domain of q of x and q prime of x is x belongs to the set of real numbers such that x must be less than negative 1 or x must be greater than positive 1. So the thing that was more complicated in this step was when we factored out our common factor. It was a fractional, but again, it still left us with a whole number exponent here, and this whole one was factored out, so that made that easy. And then the other thing that happened is when we took this guy into the denominator, we had to apply our rules for rational exponents. I guess a third thing would be, since the denominator was a square root of something, that meant it wasn't just x can't be a certain value, it meant that this expression x squared minus 1 must be greater than 0. So our restriction ends up looking different in this example as well. Example 3 asks us to find the equation of the tangent. So we're not going to do the whole thing. I'm just going to do the differentiating. You know how to find the equation of a tangent. We'll talk about the steps quickly, but I'm not going to do it. Equation of tangent to y equals rational function x squared minus 3 over 5 minus x, and we're finding the tangent at x equals 2. So following our steps a little more quickly, we're going to turn this into a product function. So we have x squared minus 3 times 5 minus x to the power of negative 1. Apply the chain rule. So we're going to take, and maybe I won't even write it down, we'll just do it. Chain rule says take the derivative of the first function, which is 2x, multiply it by the second function, 5 minus x to the power of negative 1, add the product of the first function, x squared minus 3, times the derivative of the second function. In order to do that, we need to take the derivative of the outer function with respect to the inner function and multiply it by the derivative of the inner function. So hopefully we're getting better at that. Now I'm looking for I could be looking for a common factor, but this example even just says, hey, leave it like this, because now all you're going to do is sub in the value of 2 in order to find, so sorry, this is now y prime, or y dy by dx. Now all we're going to do is sub in the value of 2 in order to find the slope at this point. Then we're going to sub the value of 2 into the original equation to find the tangent point. From there you'll have the tangent point and the slope of the tangent. So then you just go slope point formula, point slope formula in order to find the equation of the tangent. So maybe just next steps, ... sub x equals 2 into y prime to find slope of tangent. Sub x equals 2 into y to find tangent point. Then use point slope formula to determine the equation of the tangent. And point slope formula looks like this: y minus y1 equals m times x minus x1. Okay, example 4 has to do with the price or cost or value of a new car t years after it is purchased. So it's depreciating in value, and that is represented by the function v with respect to t, value with respect to time, is equal to 50,000, it's a nice car, plus 6t over 1 plus 0.4t. Okay, so a rational function that represents the value in dollars of a new car t years after it is purchased. And what we are asked to do is determine the rate of change in value at 2 years, 5 years, and 7 years after purchase. We're not going to do all those, but all that's suggesting is that, and we kind of know what we're going to find out, the value, if we drew this curve, is going to look something like this. So basically in the 2 year, it's going to be depreciating quite significantly. The rate of change is going to be drastic. Then after 5 years, it's going to continue to depreciate, but not as quickly. And after 7 years, it's going to look something like that. So the slope of the line, the slopes should be negative each time, but they should be negative and increasing. What does that mean? Well, between year 1 and year 2, there's going to be a big price difference. Between year 5 and year 6, there's going to be a less price difference. And then the years 7, 8, and 9, and 10, there's even less significant price difference. So that's what we're looking at and what we're looking for. Step 1, differentiate. We're going to express this as a product. So this is 50,000 plus 6t times 1 plus 0.4t to the power of negative 1. Then the derivative is, product rule, it's the derivative of the first function, which is just 6, times the second function, 1 plus 0.4t to the power of negative 1, plus the first function, 50,000 plus 6t times the derivative of the second function. And we're going to be looking at the chain rule. So we've got the derivative of the outer with respect to the inner. That's a negative 1 times 1 plus 0.4t to the power of negative 2 times the derivative of the inner, which is 0.4. From here, we are going to simplify by pulling out our common factor. So we have a common factor of no numerical common factor really, but just this piece, 1 plus 0.4 t to the power of negative 2. What's that going to leave us with? The first term, that's going to leave us with 6 times 1 plus 0. I cannot say that, 1 plus 0.4t to the power of 1 plus whatever's left in the second piece, 50,000 plus 6t, close bracket, the negative 1 and the negative 0.4, positive 0.4, we can kind of put together into negative 0.4, and that's it, because both of these factors, this factor has been factored out. Continue simplifying. 1 plus 0.4t to the power of negative 2. And then inside here we've got distributive property. 1, 2. That's 6 plus 2.4t. And if I do this all, I'm not actually going to need those brackets. And then here we have negative 0.4 being distributed to 50,000 and to positive 6t. 0.4 is 4/10 or 2/5, however you want to think about that. So this 50,000, when it gets multiplied by 0.4, is going to be negative 20,000. And this 6t is going to be negative 2.4t. And to simplify that, I'm going to do 2 steps at once. I'm going to put it back into a quotient with anything with a negative exponent in the denominator. So 1 plus 0.4t to the power of 2. And then in my numerator, I see we have positive 2.4t and negative 2.4t. And we have 6 minus 20,000, which is negative 19,994. Dun, dun, dun. That is the derivative of our value function. So that is the rate of change of the value of the car, which we can now, if we wanted to find, for example, as it asks us, the rate of change of the value of the car at 2 years, we just sub a 2 in for t. So we'll do one of these. Just copy it down. Negative 19,994 over 1 plus 0.4 times 2 squared. I'm going to work across even though it's illegal. Over 1 plus 0.8, that's 1.8 squared. And I would put that into the calculator, and you would end up with negative 6,170.99. So at the second year, the car is depreciating at a rate of about $6,000 per year. Right off the lot, it's depreciating quite heavily. I'll just give the answers for the next two so that you can have a reference. But the derivative of the value function with when t is 5, so at 5 years, ends up being negative $2,221.56 per year. And the value of the derivative function at 7 years is negative 1,384.63. This is fairly realistic. Other than sometimes they do a double function, because pretty much if you buy a new car, as soon as you drive it off the lot, they say it drops like between 15 and 20%. So your resale, you drive it off the lot, you drive it back on the lot, it's not worth the same amount of money. It's not a new car anymore. So after that drop, then it kind of follows this trend. Good, good. A couple of other things to talk about. What was the initial value of the car?
$50,000.
$50,000, okay? You could find that out by just looking at what it is, but also if you subbed in 0 for t, the value of the car when it's brand new would be v with respect to 0, in which case you would have this term would go to 0, this term would go to 0, you'd have 50,000 over 1, which is 50,000. Okay, let's make a note of that. B, initial value is $50,000. And C, explain how the values in part A, so our derivative values, can be used to support an argument in favor of purchasing a used car rather than a new car. That's pretty straightforward. What lots of people actually do is they just look for cars that are 2 to 3 years old, and they drive them for 3 to 5 years and then sell them again and then buy another one that's 2 to 3 years old. Newer cars have less problems. So when you get a car that's like 5 to 7 years old, it starts having more major problems. Whereas from 2 years to 6 years, your car doesn't need as much attention. And you end up cutting these first big losses after 1 year. What is it? It's probably something like $10,000 in the first year. So that's a pretty expensive year to own a car. So don't do that. Practice problems that you should be able to do from 2.5 come from page 124. And you should be able to do 1 through 13, or at least understand them. Thank you very much.